Okay, thank you, and thank you for being here after lunch. Okay, so I'm going to talk about our latest work on quantization of heat flow in various fractional quantum Hall states. So I will start with 0th Landau level, and then I will move to first excited Landau level. And my job is to make you believe that we found Majorana by some orthogonal approach rather than what you, I know everybody of you are aware of Majorana fermion, and all of you know what is a semiconductor, superconductor, and how to catch them. While they are debating about they could or they couldn't catch Majorana, we think we did. So I want you guys to be with me for this 40 to 45 minutes. And of course, it's a very flat work, like it's nothing exciting or exotic. It's thermal conductivity, like maybe you did it in your undergrad and stuff just to measure electrical conductivity. I was measuring thermal conductance. And the only fancy thing is my sample has to be cooled down to low temperature and has to put in a high magnetic field. Everything else is very simple. And these are my collaborator, by the way, but this is my boss, and I must mention that he was my lab mate for last 2 years, while most of the work I was doing with him. And this playground slide is actually the scheme of our experiment. So we have a hot reservoir and a cold reservoir, and of course heat flows, we know. So all I do in my experiment, I measure the temperature of this hot part and the temperature of the cold part, and then some fitting, and as I said, I will ask you to believe me at the end of the day that we saw Majorana fermion, okay? So let me just remind you, as I said, that you know about conductivity measurement. When we say electrical conductivity, everybody knows. So it's a classical conductor. You subject it to potential difference or temperature difference, so current or heat will flow. And then we are also aware of the fact that how the electrical conductivity will look, and similarly thermal conductivity. And also we know about something called Wiedemann-Franz law, and which basically gives the ratio between these two. And I think we also know about this fantastic constant which is known as Lorentz number. So as we flow through my talk, we will see what happens to Lorentz number if we go from electron to something which is fractional charge. And that's all about it. Okay, so as I promised, it's a quantum of heat conductance. So I want to be in quantum limit, and what is better than 1D ballistic quantum wire to start our quantum discussion. Okay, so it's long back, almost more than 35 years back. John Pendry published this paper. This paper is about quantum limits of flow of information and entropy. And in this paper, what he actually did, it's very simple. So basically, he used second law of thermodynamics, and he clubbed it with energy uncertainty. And this basically sets an upper limit to the heat or energy transfer in the 1D ballistic system. So I'm not going to repeat many times 1D ballistic system anymore, because so far my talk is concerned, it's all about 1D ballistic systems, okay? And it's a very strong statement that it states a universal upper limit, but on top of it, what he claimed in this paper, that it really doesn't matter what kind of particle is carrying the heat. So this is really amazing, because be it boson, be it fermion, the upper limit of heat that is going to be carried by them is same. So this is pretty exciting by itself. And this is in short what he means. And then if I look into 1D ballistic transport, I just want to give you a hint, like if JTH will be the current flow, like heat current, then this is a known equation that we know, all of us, like this is it. And what he talked about is this kappa naught T. So far I'm not going to talk about T all the time. I'm going to concentrate on this prefactor of kappa naught. And this kappa naught, as you can see, is only fundamental constants. So it's really, and if this number stays constant for fermions and bosons, it's really a strong statement. So of course we want to prove it, and this is the number, by the way, it's something like a picowatt. And this is, if I integrate this equation, this is what it gives. And as I said that in my experiment, I eventually will measure temperature and work with this equation further on. So pretty simple. I'm going to only measure temperature. I know how much energy I'm dissipating, and I'm going to show you what I get eventually. Okay. So again, so Wiedemann-Franz law in ballistic 1D channel, if we have non-interacting electrons, we know that now we believe that this is the thermal conductance, and this is the electrical conductance we know, and we are not surprised to see that Lorentz number is still valid. So for electron, Lorentz, like Wiedemann-Franz law is valid. So we are going to look if we will be going to a strong interacting regime, what happens to this, if it will stay same or different. So basically this was, as I said, it was predicted 35 years back, so people were not sitting down, they were doing something about it. And so the first work was done in Caltech, and then following them from phonon, photon, and this work was done in a French group, which by the way is the work that motivated me, and I'm just doing similar things to what they did. And they proved even for electrons, the Pendry is right. So basically bosons and fermions are already proved. Okay, so basically when I started the work, as I said, everything was proved. So
sorry, can I ask you a question?
Yes.
Can you describe this experiment with the photons?
The photons? Yeah, so these are, they basically deal with, superconducting circuits. So they can basically have single photon modes in the system. So that's what they showed. You will see that they are not one, but they tend to go to one, and that was the experiment. So, but for electron was done in integer quantum Hall, and we followed it through to fractions. And why? This is the next. So basically, as I said, for non-interacting bosons and fermions, it has been already proved that yes, they carry the same amount of heat. Okay, so what's next? So let's ask this question: if interaction is there, if this fundamental, quantity stays really same or it changes? And looks like that yes, it doesn't change, and that was done again 30 years back by Ken and Fisher, and then they showed that really if we go to 1D ballistic channels in fractional quantum Hall, which is a strong interacting regime, yet it should not change. So basically this is a very strong statement, and I believe that this work was waiting for me because as I said, it's a long, old prediction, so I got just lucky to do it. And of course, Wiedemann-Franz law breaks down because now the charge or the conductance is fractional, but the thermal conductivity stays the same, so Wiedemann-Franz law is no more valid. Okay. So for us, as I said, the 1D interacting system will be the fractional quantum Hall effect. So I don't know what about you guys about fractional quantum Hall and stuff, so I'm not going to dig in deep. Just trust me, in fractional quantum Hall, the edge states carry fractional charges, and that's what I want from you to believe me. I can go in details, but I don't know. So as we all aware of from our undergrad, quantum Hall is like a 2D electron gas subjected to high magnetic field in low temperature. Eventually we have multiple number of like one or more edge states, and each modes basically carry this E square over h when it's integer quantum Hall, by the way. And these are the ballistic channels that we are going to consider for our heat conductance measurement.
So, sorry, so you actually have a 2D sample?
Yeah.
Or, okay.
But my bulk is wood. My edge is only conducting current. That's a very good assumption, like no walking through, we are good. Okay, so this is it, this is the thing. So let me just remind you a few things, maybe many of you know about it. So in bulk, as I said, the bulk of QHE is insulating and has localized quasiparticles. So namely, it doesn't really conduct heat or electricity or anything. And edge for integer quantum Hall has 1D chiral modes, where as I said that if the conductance is nu E square over h, the nu is 1, 2, 3. Similarly, for fractional quantum Hall state, we have 1D chiral edge modes, but the conductance of these chiral edge modes are fractional, and mostly they are odd denominator fractions. As you can see, it's 1/3, 2/5, 2/3, 3/5. And there are some non-abelian states, which are, as you can see, one of them is 5/2, which is even denominator, and one time very celebrated because it was said to have Majorana fermion, and this is we are heading to eventually. Okay, so bear with me. Okay, so integer quantum Hall is straightforward because the non-interacting picture is very good. So you have just edge modes which are electrons and perfect. Now when we go to fractional quantum Hall, there are particle-like states like 1/3, 2/5 where you have only downstream charge mode, but then there are some Hall conjugate and also these non-abelian states which can have some upstream modes. Namely, when I say downstream, it's in the it's in the like as the potential difference goes. So the current flows there towards the ground. Upstream is like something flowing from the ground towards the other direction, which in terms of electrical conductance, it's not so easy for us to think because wow, how? So but they are typically neutral. I will talk about it what this neutral mode means. So in short, in Hall conjugate or non-abelian states, there are counter propagating edge modes. So that's what makes the story more complicated. So far so good. So what are the states that I am going to talk about here today? So one will be 1/3, which is the lowest Landau level, the Laughlin-like state, the basic one. And also I am going to show you some results for the Hall-like counter propagating states, which are 2/3, 3/5 and 4/7. They are interesting and important for me because what I am going to do is like I am going to prepare my case for my non-abelian state, because they also host some neutral mode, and I think all of you are aware of that Majorana is also a neutral mode. So nobody can get it through electrical measurement directly. Yeah. So these are the states that I'm going to show you my results. And let me tell a bit of details about what Ken and Fisher basically predicted when they predicted for these strongly interacting 1D ballistic edges. So the prediction is like this, that as in case of 1/3, it's the lowest Landau level and it has one composite fermion edge. It should have one unit of it as one electron mode. In 2/5, it will have two composite fermion modes, so it should carry 2 units of it. But 2/3 is a special case, as I said, that it has one up and one downstream. So basically, technically, it should be 0. But when I say this 0, 1, 2, 3, trust me, this is thermodynamic limit. You are giving it time to, for it to be 0, it has to be like a long length limit that we are talking about. And 3/5 should be minus 1 unit of heat, which is a bit strange, like how come heat can go from cold to hot. I will talk about it when we go into the details of the experiment. But these are the predictions that they did in their paper in 97 and which we looked into in our experiment. Yes.
What do you mean by the thermodynamic limits? So you're worried about edge modes coupling between the two edges?
Yeah, but it's basically the thing is that if they will be super coupled, I won't get distinct two edges, right? Yeah. So in order for me to get two edges, they should not be coupling like anything, but there should be some.
It's normally an exponential.
It will be when it will be non-equal. The 2/3 is a special case when you have exactly equal and opposite. So that's why I said infinite. That's why the limit is. But yes, that way. Okay, so I'm talking about 2/3 a bit more because 2/3 is going to give me a way to prove my point in 5/2. So as I said, that the 2/3 is a Hall-like state, and the non-equilibrated picture is something like you have a 1 downstream and 1/3 upstream. Okay, so this picture was drawn by Alan MacDonald back in 1990. So the story is like this, that you have a full Landau level and you have 1/3 of it is holes. So you look at it like this. And if you measure a 2-probe conductance, electrical conductance, it should give you not 2/3 G naught, G naught is E square over H, but 4/3 E naught E square over H. And experimentally, no one saw that number. Okay, so basically, but no matter what, as I said, the 2 counter-propagating edges, if you have a long enough sample, k should be 0. That's the prediction. But as people didn't see this 2-probe measurement, like 4-probe measurement of electrical conductance give you 2/3 G naught, but 2-probe also gives you 2/3 G naught. So this basically, again, Kane and Fisher, they said that there is some kind of equilibration going on, but also there is a characteristic length scale. They don't really mix with each other in 0 length, but they mix with each other, and eventually you get a 2/3 charge mode, which is downstream, and a neutral mode, which is upstream. So eventually now 2-probe, 4-probe, everything will give you 2/3 E square over H, and we came to know about this something new called neutral mode. So basically it doesn't really carry any charge, so you cannot catch them through your electrical measurements, but something else you have to be done. But yes.
So one question about the measurement.
Yeah.
So when you say capital 0,
Yes.
So what are you actually measuring? So you put some temperature difference between the 2 contacts, and then you measure what?
I measure the temperatures. I will come to you. We'll see what I measure. Yes, sure. Sure, for sure. I'm just giving a background for all the states so that you can believe, eventually I give you a number. Yes, sure. So neutral mode carry no charge, but for sure they carry heat. Okay, so let's talk about a bit more about neutral mode, because trust me, I also myself don't understand neutral mode so much. Maybe I'm convincing myself along with you, so bear with me. And no, trust me, it's the truth, We are still digging it in, so I can tell you as much as I know. So basically, as we believe, let's say we believe Kane and Fisher, so equilibration of 2 charge mode gives you this neutral mode, and then this they are topological neutral mode. So as I said that why this topological, which means that it cannot be that it's absent throughout. This mode has to be present throughout the edge of the sample, though it's neutral. So that means it's topological, because the fact that once you fix the filling factor of the bulk, you fix how many edges are going to run around. So just because it's neutral, it cannot vanish. It has to be there throughout the sample. That's what I call topological, nothing fancy. Okay. So they are invisible. As I said, they are invisible to conductance measurement. So I cannot be, dealing with them in my regular measurements. They are bosonic. They have bosonic thermal conductance, which tells me that they should be as good as electrons, which is 1 unit of kappa not T, same as this. And they are associated only with particular fractional quantum Hall states, namely not all states that have it, because I'm claiming they are topological. That's the thing. So basically, these whole conjugate states, which are between 1 and half, they have them, because they are whole conjugate states. Okay. So now let me motivate. This is the start of my talk, actually. So let me tell you why I want to do thermal conductance. So first of all, this is a topological constant, as I told you. It depends, determined by the bulk wave function. Namely, as I said, that for Kane and Fisher, they said for 1/3 it should be 1, 2/5 should be 2. So this basically depends on the bulk filling factor. And also, it reveals the net chirality of the mode. So I told you that 2/3 should be 0, but 2/5 should be 2. So basically, it tells you how many edges are going to run through the edges, which looks very pretty, maybe simple, but nobody could measure before, because you need this kind of measurement in order to reveal it. And then this is something sensitive to edge reconstruction. Okay, what is edge reconstruction? I talked about topological edge modes, but there can be some impurities sometimes gives you additional counter propagating modes, which can be still neutral. But it should not affect the result, because I said thermodynamic limits that we are interested in. B, these are something local, should not affect because the bulk filling factor doesn't change, and that should be something fixed for a filling factor, that what should be the thermal conductivity that we measure. So it's pretty robust. But these are true for the abelian particles. So what happens? So it will be, so for abelian particles things are pretty flat, right? I should measure something as electron, and maybe you guys can even think, you know, even that is fractional quantum Hall state, we know eventually it's electron which is there, right? It's not something fractional particle. It's the basic, like it's the interaction what makes it, you know, fractional particles. So it's electrons. Maybe that's the reason that we see. But if we have non-abelian particles, then let's say one example is Majorana, because I know everybody knows about it. So it should be half integer quantized of kappa naught. And this is something very, very strong evidence if we can really measure half quantization of heat flow, that there is Majorana present. So this is where we are heading to, and now bear with me for a few slides which may be boring.
It cannot be any filancy.
It depends on if there are parafermions, like the 12/5, the number should be 2.4. Okay. And I'm not starting about what it should be for 5F, because David is going to tell about it, and we have a spectrum of numbers, right? And we choose the wrong one somehow in the experiment. You know, it's like I can plan, but I cannot you know, train my particles to behave the way I want. So they are pretty much what they want. So that's it. So all I want to tell you that if it is a fractional coefficient in front of kappa naught, fractional multiple, that tells you that the particle is non-abelian. And it's a very robust statement. If we can do it, I think it's fantastic. Now the experiment, which bear with me, I don't know how many of you are theoreticians. I would try my best, okay? But it's a very simple experiment. The working principle, as I promised, we heat up because, you know, we are looking for heat flow. So we have some hot and cold spots. So in the fridge, as I said, we have to heat up using something. So we're heating up something, a metal. And then we are also, and let's say the temperature of this hot metal is Tm. That's what we are going to measure. And then there is a cold reservoir, of course, because heat is going to flow from somewhere to somewhere. And let's say that the temperature is T0. This also I measure. And then let's believe that in my system there is 1D electronic or quasi-particle channels which is taking the heat from here to there. And then what happens that also that because I'm in a solid state system, I cannot really deal without phonon in my system, right? So there is electron phonon also. So there is some electron phonon interaction. And so what I do, basically I give some input power. It's simple Joule heating of a metal island. And then I let my, you know, 1D channels take heat out of this metal. And of course, there is a part of heat which will go to the electron phonon interaction, because this I cannot really avoid. And let's say this amount, some amount of heat will be going through this 1D channel. Now the fact is I can change the number of 1D channel here as much as I wish, but the electron phonon should not be different, because electron phonon should be the same for this hot reservoir. This is a metal island. So that's the trick we actually adapt. What we do, we change the number of electronic channel or quasi-particle channel, which takes the heat out, and then we take the difference among them, because then what we are left with is like we can cancel out the phonon term, we don't look at it at all, and we just keep looking, you know, how many, so we know how many edges are going, we just look into, okay, what do I get? So this is what we are going to show. So let's say, as I said that, you know, it's a Joule heating, so I dissipate some power. Of course, I cannot light fire in my fridge, so the dissipated power goes through these channels and the electron phonon. And this is the equation I want you guys to keep in your mind, because this is pretty simple. This is the part, by the way, I write here only one because it's here for one channel, because if it will be n channels, you can have n here. And as I said, so by changing the number of channel here, this will be 1, 2, 3, 4, but this will remain same, and I can always take difference. Okay, so let's see how the device looks like. So this is a schematic of the device. As I said, that I have a metal island, and in my fridge, the cold reservoir is my cold finger, so I just clamp it with my cold finger, and I can have multiple channels. So basically, I put some current, and then current passes through the other edges, and there is some dissipation of power which heats it up. It heats it up to some temperature, and then the temperature of the cold ground we know. So rest is basically modeling, I would say. Yes, please.
Temperature of the metal island, you have to stabilize it to the same
So this is the thing that, you know, it's a small metal island. You put some current, and some current is going out, and you have a voltage drop, which basically gives you this dissipated power which heats it up. Yes, basically this, but this time scale is very small in order for in which time that we measure. Yes, equilibration is important. Yeah, I'm going to go through few points, but I'm not sure how many people will be interested in experimental details. So for you, for sure, yeah. So as I said, we measure only temperature. I do not measure anything else but the temperature. So what I measure is basically the electron temperature of the cold ground, like your question, T0 and Tm. And I know what is the power dissipation, because, you know, I'm doing Joule heating. So I know J, the left hand side, I know the right hand side. I plot a straight line to find the slope for the prefactor.
Is T naught fixed or is Tm fixed?
T naught is fixed. Yeah, because, you know, I'm doing Joule heating, so I can change my current and I can heat it up to any temperature I want, but cold temperature, yes, it's fixed. My entire sample is seeing this temperature, except for the island which I heat up, and I allow these channels to take that heat, you know, to cold ground.
I don't really know the thermal measurements, but is there any version of lock-in or anything? Do you have to lock in?
I use a spectrum analyzer. I will say how I measure it if you care. Yeah, sure. Yeah, I mean, like lock-in is pretty slow, so we measure through spectrum analyzer because our measurements is in 1 megahertz, not really terahertz, gigahertz, but, you know, just to avoid the noises in low frequency. That's all, nothing else. Just to make it more accurate. So this is the equation. So delta P is what I know, because as I said, it's Joule heating. You know, I know how much current I'm putting, and it's a simple circuit. You know, it's just okay. It's Hall resistor, but it's resistor Kirchhoff. So we know.
Sorry, I'm just confused about something. You know that you're measuring the electron temperature
Yes.
and not the phonon temperature?
Yes, I'm measuring the electron temperature because I measure. Yes, you know, the electron and phonon is very much coupled when the temperature is around 100 millikelvin.
So you are assuming that they have the same temperature.
So the thing is that when I'm measuring it, actually I will show you that the electron phonon, if you looked at it carefully, phonon was T to the power 5. So I am going to do my experiment not in kelvins, but it's 10 millikelvin. So the phonons are not interesting and not needed. And of course, as you know, that because the electron phonon interaction is very low for lower temperature, I have to wait for a couple of days for my electrons to cool down. Okay. So yes, they are very much decoupled in that sense, yes. Okay. So this is the equation that we are interested in, and I wrote capital K instead of small kappa naught just to say that it has also the number of channels in it, because each channel will be kappa naught. So this way. So if we can somehow get rid of this portion, then we have, if we plot, you know, delta P versus T square, we should be able to see through the slope of the graphs what's the prefactor. Okay, that's what we are heading to. So if it's small t, as you said, the phonon term is irrelevant for us because square and 5, it doesn't really bother us. But yes, when it's high temperature, we have to subtract it. We do both basically. We look into our data in various regimes just to be, you know, sure about it. And K is what we are going to determine. That's about it. Okay, so how do we measure temperature? This is something technical about my experiment. So we use short noise measurements to measure T0, and excess temperature, or Johnson-Nyquist for the thermal, like we measure thermal noise to measure this Tm. We know T0 a priori because this is what we do. We first stabilize the cold reservoir, we see that it is stable and good, and then only we start heating it and we measure the other temperature. That is how we do, because it is very important, as you see that I am going to depend on this fitting. So, if any of them are not stable, it's just not working. It will not work. It will never give you a straight line. It will be something different.
So you're measuring the temperature of the metal that is connected.
Yes,
with,
yes.
I see.
Yes.
So is there any kind of impedance issue in
So this is experimental details. Yes, of course we want it to be a very low resistive, high capacitive metal, which is a small island at the same time. I don't want it to be too small so that electron comes in and goes out without knowing the temperature, or I don't want it to too big to have huge electron phonon interaction to heat it up with lot of current. So this is the details that you do. I will tell. I will not I will tell you for sure if you want to share the pain. So this is measuring T naught. It's short noise. So I know that short noise is something also maybe you guys are aware of. So what we do, we have some simple QPCs which we get free in our structure, because we are doing these structures, mesoscopic devices. You can put whatever you want on your device as you wish. So we can, in the same device, we can put what we want to. So all these tests that we want to do, we have in the same device basically. So we check everything in the same device. So the short noise basically gives us from the from the rounding sometimes, or what I do generally, I take a straight line and I see where it cuts the current axis, and from there I just get the temperature. So this is how I basically get the electron temperature before I heat the reservoir, and then once I heat it, it's basically current fluctuation is what I measure with a cold amplifier, and I change the bias, namely the Joule heating is, I change the current and I measure the noise, which by the way, I have some prerequisite before I start the experiment, and I will be talking about it soon. So basically straightforward, I measure some noise, which is Johnson-Nyquist, and this is one of my data set. And what I do is I know from this current how to go towards the power dissipation delta P, because it's a known circuit, as I said. And from the noise that I measure using this formula, I can always get Tm, and T0 is, as I said, I know from before, that's my first requisite, that the system is stable at one temperature. This we have to measure for a few times to be sure. And then it looks like this. So delta P, Tm, it looks like this, and you can have for different number of, so this is n here is number of channels, so I can now have different number of channels to have, this is what I was talking about, so I can vary the number of channels. And because electron phonon interaction only depends on temperature, so if I subtract them at the same temperature, I will be left with as many channels are taking the heat out. So that's the idea, yes?
You could try to scale it. So it doesn't look like any good power law, or?
It's basically, if you look, it's T square, because that's the.
So it follows T square.
Yeah.
But I mean,
Yeah.
I cannot fit parabola.
Yeah, it does, but as I said, like if even there is some T5, depending on which temperature T phonon is there, if it's high, it's T square mixed with T5. If it's low, then it's T square, yes. But I don't want to go into this. I right away subtract in order for me to see, there is no phonon. That's a good thing. So it's something like this. So I can keep changing the number of, channels which takes the heat out, and I know the temperature where they are same, so I just subtract all of them. And eventually this is how I get rid of this, and I am left with that. So this is one of the results. You just subtract these two graphs, and this is what you get. And trust me, now on I'm going to only show you straight lines where may or may not the slope will be different. And that's all I have, by the way. So it's pretty flat, as I said. It's that way. So the left axis, as you can see, it's just a normalized power that I dissipate. I normalized it with kappa naught so that I can directly take the slope to kappa 0 or its multiples. And this bottom axis is Tm, and this offset is of course T0. Yes.
Maybe I want to show some picture or of your device.
Yes, I'm coming there. Yeah, I just say, yeah, I want to build up the story nicely, you know. So I don't want people to just rattle away after seeing my device. Oh, not interested. So this is my device. So you know, I don't want people to run away. I want you to stay. So, so as I said, like we can of course have many mesas. So all this 4 part that you see is like 4 different 2D gases, like the four devices which are actually clubbed together but joined together with this metal island in the center. So this is the metal island.
Where is the quantum hole?
The quantum hole is everywhere. You put this device in high magnetic field, low temperature, the edges are going to, yes.
So it's again, it's the single hole with edge contact.
Yes. But the center hole, this small ohmic contact is important not to, so my idea is that these 4 parts are not connected with each other except for this metal island. This is important because.
Basically, where does the edge states live?
Oh, edge states are here. You can see the arrows. These are my edge states. Okay.
The hot one is the pink thing, the red or the brown thing.
This is one of the edge. Let's say this is nu equals to 1. So you have only one edges. Okay. So one edge is going. I'm sending also the current through it to heat it up. And then after it is, you know, after current goes here, because the 4 are equivalent, so 1/4 of current is leaving on all of them. Okay? Maybe my color scheme is not so smart. I made dark red, light red and stuff like that. So all I mean that these are hot edges which is coming out of this small ohmic contact, and the blue ones are which is coming back from the ground. Because you know, for quantum Hall, the edges are always running, right? It's all over there. Is it okay? Okay.
But the symmetric scattering matrix is not important, right? So you know, you said that they are all equivalent. You know, you really don't know how it scatters.
I'm not talking about here scattering. I just want to tell you that I have 4 Hall bars which are connected at one point. I'm a point, you know. And the point is my metal island. So anything like goes from one mesa or one edge to this metal island now get distributed equally towards all of them. That's the idea, because otherwise I cannot get to the power dissipation.
But yeah, that's one question. Is this equal distribution important? Because I mean,
Yes.
Why is the symmetry?
It's equal. Equal is the important for me for one thing, that you know it will be equal by thumb rule because I will be sitting in all of the 4 mesa in the same filling factor, because this is how I'm going to change the number of edges. I was telling you that I can change the number of edges, but you know, if I sit in one filling factor, there is so many edges that I can have in one mesa to change. So the reason is that this fancy structure is actually allowing me to have multiple of the same filling factor edges. Namely, if I am going to filling factor 2, okay, let me actually go to that. I just wanted to. So this is, sorry, this is a actual device, but let me go to, yes. So here the 8 structures that I draw is for filling factor 2, okay. I will go back to all the slides, but you see that everyone has 2 edges. So they are equivalent. I have 4 Hall bars which are equivalent to each other. This is what I want, because this will give me the handle to change the number of edges which is taking the heat out. Like here, what I did, I closed this one and that one, so these 2 Hall bars are not doing anything in this particular scheme. And out of the 2, only one is carrying the heat in, and only one is taking the heat out there and there. So eventually 2 edges are taking heat out, but in 2 different mesas. I can draw for you the power dissipation for sure, but this is the point. Like, the thing is that I wanted to have multiple copies of my same Hall state just to have more handle to change the number of edges. But think about it, otherwise if I am in filling factor 1, I have 1 Hall bar, I have only 1 Hall, I have only 1 edge. So how do I get rid of the phonon term? So this is just a trick. Okay?
So quick question, where's the noise being measured? Is it?
It's in the drains. It's in the drains. We have this LC circuit. It's a drain. It's a floating contact where I have my cold amplifier connected.
You're also heating the metallic iron
Yes.
through the edge.
Edge states, yes. Because I don't need extra conductor. In Hall, this Hall effect, this is the beauty, you know. You have edge states which won't dissipate and will take all the current that you give it to it, it will take it. So
one more question, how do I know there's no electron phonon coupling going along inside the Hall bar itself?
Yeah, that's that.
yeah, so that's a good question, but I will tell you that I'm actually measuring the temperature through Johnson-Nyquist noise of this metal island.
No,
so
but
all
measuring the current noise through
yes, that's good, but the noise is conserved. Yes. What I'm doing here is look, the current is conserved. I'm not losing any current, and the noise is also conserved. And I'm measuring, by the way, in megahertz, not in gigahertz, that there is some dissipation, you know, that let me lose some information. No, I don't lose.
Would you repeat the argument again? How you know there's no electron phonon coupling inside?
No, I'm saying that I don't care about it. I'm measuring the temperature of this metal island. That's what I'm interested in. I'm not interested in all this loss of energy, you see? And that's what makes this measurement really, really robust. Because even if I lose, you know, first of all, current is conserved, and what I'm banking on, this noise is also conserved. So I measure something which is conserved.
But you're also assuming that each of the mesas are going to be exactly the same as each other, right?
That I had to skip in order to reach this schematic, but I will show you that I'm not goofing. I really do this, yeah. Trust me.
So how do you know there's no some resonant impurity in one? In one
You can do
method
it. Let me convince you. Thank you. Okay, so all these fancy figures that I made, just to tell you that I have these 4 different Hall bars, and I have these QPCs that we call, or you can name it simple gates, which can be used just to close it, so that no current is going to the drain in this particular Hall bar, and namely it's not taking part, or it is taking part. So how I do it? Basically, I can just pinch this gate and let this edge to be locked and not go to drain, and it doesn't affect my result. And this is how I basically go from n equals to 4 when all of them are open, to n equals to 3 when only 3 are open, or n equals to 2, you know. This is what I wanted to do, and that's why I have similar copies of Hall bars next to each other. Why it looks like a cross, it's just for my convenience to draw it. It can be anything. So this is the complete structure that I have, because I have to do a lot of tests, as you said. So, and the list of tests are these. So before we do the experiment, we have to go through a lot of tests. Like you said, that the current has to be equally. So this everything. I have to make sure that all the 4 Hall bars that I have, they're equivalent to each other. Because you know, that's something that we are working on. But more important, I think, is this one. The electrons are fully equilibrated with the small reservoir. Because, you know, I told you that I am measuring Tm. But as you said, that how do I know that this Tm is the right temperature of that hot reservoir? So yes, so this was not trivial. So we had to find out the right size of the island and everything, you know. There are many more layers, which is only painful for me and not amusing for you, so let it be. But yes, we take care of the fact that it is like that, and also that this is also another important thing. We are measuring noise. So I cannot allow my device to have any other noises than the Johnson-Nyquist noise that I'm measuring. This also I verify. So, this device is faceted with all these multiple contacts because of that. Like first you check all these things, and if all the bullets are good, then only it goes to the next level that we measure. Okay? And no presence of bulk energy modes. So basically, this is not my assumption, because we can also check it, and also that we look at the Hall plateaus and everything to see the state is well developed or not. This is also important for us, because when things are going through the bulk, it can reach the ground before it reaches the amplifier, because I'm banking on the fact that in my measurement scheme, the edge is taking my noise, like all the noise is taken by edge. So if bulk is conductive in a way, then something will be drained through the bulk and will not reach my amplifier, and I will be measuring something wrong. So that has to be also there. And length of the arms are like the Hall bars are limited because of my lithography, but this is also important, why later on I will tell, and David will also talk about it, and namely this thermodynamic limit. And also like this equal splitting between the arm, amplifier gain, contact resistance of the small, everything has to be checked for sure. Yeah, it's the straight line comes with a pain, not simple, but it's straight. Okay, so now I will show you the result. So I hope everyone is with me except for those who doesn't want to, and so no, I'm fine, doesn't matter. So I'm going to show you the result for 1/3, because that will be the result for what Ken and Fisher said, that the strong interaction should not affect us, and this will be a good thing if let's see what happens in 1/3. And then also I'm going to look at 2/3, 3/5, and 4/7, which are the whole conjugate state, and as I said, that these states are going to advocate my case for my 5/2 results. Okay, so be with me. This is again I showed you. So this is just this is filling factor 2. This is my result for filling factor 2. So the French work was done in filling factor 3 and filling factor 4. So I first did it in filling factor 2 and 1 to see that that this result is robust and my devices are working exactly well. So these various lines are basically for delta n. Delta n is the number of edges which is effectively carrying the heat. So as you can see, and the inset is basically the slopes of these each lines. And as I draw a straight line through it, I see it's very much close to 1. So this tells you that yes, filling factor 2, you have electron channels, and they are all good as it was before known. So our ground is ready. And 1/3, as I said, it should have only 1/3 one channel, and it should be having a single edge mode in this state, and kappa should be kappa naught. This is what Ken and Fisher said, and this is what I got. Okay, so I got 1. So happy? I don't know, people look clueless, never mind. So the thing is, actually you prove that having strong interaction in the system really didn't matter. Okay? And good for me too. So let's see what happens for the neutral modes, because 2/3, 3/5, all these states have counter-propagating edges. So the first thing will be they are more complex, and I think I measured all of them before, so I skip. And these 3 states are what I'm going to show you. So 2/3 has exactly equal and opposite number of edges. 3/5 has 1 more opposite running edge. 4/7 has 2 more. And this negative sign, yes, it's something bothersome, because heat cannot go upstream. But then think about it that in quantum Hall the edges are running through. So there is another edge on top where it is, let me draw it for you, because this is something I like. So this is our Hall bar. Let's say this is the metallomic contact that we have. So for 3/5, let's say, we have 1 downstream, and let's say 2 upstream, but the edge continues. So there are 2 neutral modes which are now this side going from hot to cold, and only one charge which is coming from cold to hot. So this is the edge for 3/5, 4/7, which is going to actually carry the heat, because you can see that both my edges are shorted with the metal reservoir. Okay, so that's the negative thing, nothing fancy. Okay, so far so good, but why 2/3 should be 0? I think I explained to you why 2/3 should be 0. It's just a schematic, like you have one edge going to. Actually, this is the thing that I drew, so I'm not going to spend more time on it. So, but I didn't measure 0. I measure something like 0.33, but it is for both the edges. You have to divide it by 2 in order to get for one edge. So it's 0.17, something like that, not 0. So it's not 0. Yeah, it's not good. It didn't make me happy either. Yeah. And then we did so, and for 2/3, if you measure 1/3, it has a ring in it, right? It's 1/3, 2/3. You think, oh, maybe this is the quantization. 1/3 is the quantized number and stuff like that. Okay, so if it is quantized, it should not change with temperature. So because I cannot change the length of my sample once I did it. I mean, I can of course make a new sample, but in this one I can change the temperature. And this change of temperature is the cold reservoir temperature that I am doing. Okay, so I am heating the entire electron bath of the sample, and on top of it I will be heating it up just to see this effect. So if you do it, you see, oh no, this is no some holy number, it changes. So it has to do with the equilibration. You increase the temperature, you let them interact more, and they are reaching. So basically, when I'm here, it's by 2 will be 0.1 almost, each edge, close to 0, but not 0 yet for sure. And then we go to other fractions, and you can see for 4/7 it should be 2, but we are kind of close to 2. And for 3/5 it should be 1, we are also close to 1. But 2/3, as I said, it's a bit different. So we have a very naive way to explain it. Like I think I already did it here. So 2/3 is a special case when you have an equal and opposite number of equal number of channels which is interacting. So what happens that it needs to be infinite length in order for it to really make it 0, to give all the heat back. But for 3/5 there is one more extra, so it makes it exponential. So what happens, that things looks like this. That 2/3 goes to 0 for a real long length, and my sample is somewhere here. But for 3/5 and 4/7 it reaches the quantized value faster, because there is non-equal number of edges which are effectively carrying the heat. Like that's the deal.
What side?
What
What is side?
This is the characteristic length we wanted to for this equilibration.
So what
So we calculated something like 30 micron or something. Okay.
where does it come from?
So basically you here okay, so you can say take it like this. Here basically what I do, like this is the equation, if you okay. So basically you just consider Newton cooling, it's JT, and just because the right hand side is 0 for 2/3, it's linear, but for the others it will have some t dependent term which makes it exponential, and that's it, nothing else. Okay. So okay, good. So I think we can say now that 1D electrons and 1D fractional mode, and even for 1D neutral mode, I want to take this seriously, quantize thermal conductance in the same value. Okay? Because I want you to remember this neutral mode, because Majorana is also neutral. If it will be 1, I cannot say that it's Majorana. Here we say that all of them are equal, and let me now go to the first excited state, which is very exciting. And I will be done because David to follow and he will be only talking about this. So I'm good, trust me. Let me just show you the data. David will actually give you better sight into it. So this is a normal Hall scan, like, you know, this is the conductivity and this is the RXX. And this is a bad sample. This is not a very good sample. This is not the sample that has this 36 million mobility and people measure U over 4 charge and stuff, because there I measured 2. I get the number also same as this, but there was some parallel heat conductance. So we were looking for something because, you know, I'm talking about some half, you know, and you understand by now the experimental accuracy has some limits. So if you want to really claim something, you have to be really, really careful. Otherwise, people are sitting there to kill you. So we went to, no, it's true, you know, we know this. Everybody wants to kill you, you know, this is what we want, you to be dead. Okay, so we go to a bad sample. It's not bad because, you know, seeing 5.5 is good enough of level for the sample that it's a good sample. What I'm saying that the mobility, my collaborator Vladimir is not happy about, because, you know, he does 35 million and I want something 40 million to do my life. So, you know, this is something mediocre for him. But what I want to tell you that I just didn't want to measure in 5.5 because there is 7/3, which is a particle-like state like 1/3, and 8/3 is something like 2/3. So we want to also verify ourselves in the other 2 states. And also I did it, of course, in filling factor 2 and 3 just to be sure, okay, electrons are really electrons in this system, not something else. You never know. And let me tell you something in brief. Maybe David will, yes, please.
What is this peaking green?
This green? Oh, these ones. Okay, this is some reentrance state, I'll tell you. Okay, so it's like it goes to filling factor 3 again. If it's a very clean and good sample, you have this kind of striped phases. I'll tell you later on, okay? It's a signature of good sample, by the way. So in better sample, you will have tens of these, actually. So let me tell a few words about 5.5, though I'm sure David is going to talk about it. So it's like the half is something like this. So composite fermion picture is like this, that you have electrons, and every electron catches 2 flux quanta. And that's what we call composite fermion. So think about it, if it's even denominator state, that means that you have exhausted all the fluxons, right? So all the fluxes are now attached to all the electrons. So basically it's effective 0 magnetic field that you see this state. That's something interesting. So basically also 5.5 I showed you in last slide that the RXX is 0. So it's like a BCS superconductor, you know, it's like a fancy stuff. And we are all sure, I'm sure everybody knows about superconductor because, you know, Majorana is in hype since I finished my PhD. So I'm also after it, by the way. So no apologies. So this is kind of P-wave superconductor. It's not S-wave, but P-wave. And you guys know better than me, so I'm not going to dwell on it. This is how Moore-Reed looked at this Puffian state. Let me just, because the chair has showed that he wants to stick to the time, and me too. So, okay. So the thing is that, by the way, our group is working in this fraction for a long time. So it was found in our group first that the charge is really over 4. But when they put a tick there, my boss says that still there was many questions that, oh, it's non-abelian or not, nobody knows, you know. And then there was upstream neutral mode, which can also say, oh, it's non-abelian, still not sure. So, you know, this was really do and die for us. Let's see if it is or not. So I'm sure David is going to talk about all of them. So there are these prospective states. These are abelian states, and the Majorana I preferred with this dashed arrow, which are decorating this stable side, which tells you this anti-Pfaffian, or sorry, not anti-Pfaffian, I'm so much into anti-Pfaffian, non-abelian states, namely, you know, quantum computer and blah, blah, blah. You know, come on, it's going to give us money in our future. So we cannot neglect it. Never mind, to cut the long story short, it is this that they all have this 0.5. And I must say that all these numbers are basically this thermodynamic limit, namely, you let them equilibrate, all of them, and that's the number that you get. Okay, so that's the story, but I don't want to dwell on the theory much. So if non-abelian, you see, I should be able to tick on one of them, but these red dots are already for the 5 states which are mostly probable. Like these are the states which were so far, like the other experiments, kind of narrowed them down. And sorry, okay. So again, this is the result for 7/3 and 8/3. 7/3 should be similar to 1/3, so it's 2 plus 1/3, which should be close to 3, and we got something close to 3. I'm sure experimentalists will definitely appreciate this number as 3. For theoreticians, I don't know. And for 8/3, it's close to 2. Which again, it's like 2/3, it has something, but 8/3 has some RXX non-zero, which is details I can tell you later on. But okay, so every ground is ready. People are tired of me talking, so this is the results for one more check that I wanted to see again. The outer edge, the inner edge are electron or not, and everything falls in place. This is my 5-half result, and please guys wake up for a while from your phone and laptop. And there is bad stories. No, there is a bad part of the story is that I don't stick. So I show you this and I'm happy. But then no, my electron temperature here was 18, but I can go to 10. So I go to 10 and I suffer more. So I go and I keep it increasing. So it's reaching almost 3, making me worried about what did I see. But it's not bad, because if you remember 2/3, as we went to lower temperature, it's the equilibration is what gets affected. Also, I think David will talk about it. So these are some raw data, but this is all the 17 measurements that we did all together here. I don't go more than 25 just because the fact that my 5-half plateau had RXX 0 only until 30 millikelvin. It's again, experimental details which we don't need to know maybe, but the thing is that, no matter how much I love my data, but I think it's near 2.5, which 0.5 is what my focus is, and which tells you, also I did it for 8/3 a bit, that to see if there is temperature, but it's not so much, but there is some temperature dependence for sure, which tells you that the sample length can be, or some electron phonon, I don't know. So yes, this is something that makes you happy, right? And makes me happy, or my boss happy a lot, because he likes to plot it this way to just tell you that, see, we are around 2.5. And so I close my story, and this is the work that David is going to talk about. And there were a few more, I think couple of more there. Among which only Steve Simon thinks that it is maybe non-equilibrated result that I got, because the phase that the state that my data points to, it's not something numerically very probable. So, but David has a better picture for it, that how can one get it? No, I'm only apologetic about what I get, because I couldn't train my electrons well. So people are welcome to explain the data for sure, and that's it. 12th of July, our paper will be published like a paper form, but we are done. And thank you for staying awake and listening to me, if you did. And any questions?